Almost 2,000 years ago, the Greek scientist Hero of Alexandria was aware of the tremendous potential of steam, though it was not until about 200 years ago that technology had advanced sufficiently to allow industrial steam boilers to be commonly used. Since that time, the design of steam boilers has been constantly improved, and they are now used in many of today's industries to provide a modern, efficient energy system for process, heating, and power. Because a boiler works under pressure, it is not usually possible to see what is happening inside it. The terms wet steam and carryover are everyday idioms in the steam industry, yet very few people have ever seen these phenomena, and the actual water movement inside a boiler has, until recent years, remained largely a matter of conjecture. As we can only see the water level in the boiler gauge glass, and this is usually quite steady, many people quite reasonably assume that the water in the boiler is almost still and at a fairly constant level. We will demonstrate how two modern fire tube package boilers operate, one designed with an oversized shell and the other of typical modern compact design, and shows the effect of the following: normal operation, feed pump operating with on-off water level control, high steam demand, normal TDS, high TDS. Let us look at a diagram of the first boiler, which we will call Boiler A. Though this is a modern design, the boiler was specifically chosen for demonstration because it has a comparatively large shell for its required output, which gives a gentle boiling action seen in boilers of 20 to 30 years ago. This is a 3-pass boiler. The second boiler, Boiler B, could also be described as a 3-pass design, but in this case, the first and second passes take place in a single furnace tube of comparatively large diameter. For this reason, it is known as reverse flame boiler. This particular boiler was selected for demonstration because it is of a very compact design and typical of a modern small industrial boiler. Here, the inside of Boiler A can be seen viewed from the top left burner end of the boiler. Front and rear protection tubes are visible, as well as a horizontal stay brace running from the front to the rear of the boiler. The stay brace is visible at normal water level, unlike Boiler B. With Boiler B, the interior can be clearly seen with the bottom of the boiler manhole visible at center top. Behind this can be seen the low water probe protection tube. The steam nozzle is between the manhole and the protection tube, and though the steam nozzle itself is not visible, the water vapor which forms whenever the feed pump is on can be seen flowing upwards towards this point. Let us first examine both boilers working on a light, steady steam load with a normal TDS level of about 3,000 ppm. Note how even at this low, steady steam generation rate, there is considerable movement of the water and significant variation in its level. We can also see the need for a protection tube to smooth out the fluctuations in boiler levels if we are to have accurate level control. Here we see Boiler B working under similar conditions. The difference is obvious, with far more turbulence and steam bubbles, which, although large, burst quite quickly. We will now reduce the pressure in Boiler B from a normal 115 psi to 50 psi and observe the effect of firing at reduced pressure. Note the high, surging turbulence and large bubbles with water splashing towards the steam nozzle. The appearance of the water surface is typical of a steam boiler working at low pressure. The steam bubbles are larger simply because they are not as highly compressed. When the feed pump switch is on, the first thing we can see is a mist which appears in the steam space as soon as the pump starts and disappears the moment the pump switch is off. The effect is apparent in both boilers. The mist is almost certainly caused by the comparatively low temperature of the feed water, which is approximately 185 degrees Fahrenheit.